So now that we've talked about all these different models, and I believe there's actually a few more we haven't talked about, which we'll look at briefly, let's go ahead and compare and contrast the pros and cons of these different approaches. And we'll see the good and the bad of each way of doing things. So each of these programming models for the Java fork join framework has pros and cons, as with almost everything in computing. It's probably the case that this iterative fork join approach that we see here is fairly simple to program and understand. You just have two loops. Everything is kind of localized to this one place in the code. It's really easy to understand once you understand how lists work in Java, once you understand how for each loops work in Java, once you understand how forking and joining works in Java, piece of cake. However, when we run the program, you can see that the work stealing count for this implementation is significantly higher than all the other ones. So for this particular example, which was on this particular platform, the work stealing count is 31. So that's high. And this was on a 6-core Lenovo laptop. I should probably rerun this at some point. I've got a lot more cores. Maybe we'll run this for real on my Mac and see how it performs there. And as a consequence, performance is lower. So this particular result, which comes from running the test program, gives you some diagnostics about how long things took to run, the different techniques, and also how much stealing they did. And you can see here that the test apply all iter ran the slowest and it had the highest steal count. So that's possibly an indication that there's a relationship between steal count and overhead. The recursive decomposition approaches that we looked at, which were the ones that was the apply all split index, the all split, and then there was also one called apply all split index EX. That's the one where we passed in the array. They had lower steal counts, and perhaps as a consequence, they also executed more efficiently. And this is particularly interesting. The test apply all split index EX method was the fastest one, and the other ones are a little bit slower. But they were all faster than test apply all iter. So you might take away from this that reducing work stealing is a bit of a win, and doing less data copying can also be a win. But it's arguably the case that these recursively decomposed approaches are harder to program because there's just more stuff going on, whereas the approach over here we did with iterative is pretty straightforward and pretty easy. It's just a pair of for loops, whereas the recursive one takes more thought, especially the one that uses the indices. And there's also more work going on with respect to the method calls and data copying in some cases too. Another thing to note here is that the recursive actions overhead is lower than recursive tasks. That's not really because recursive action is faster than recursive task. It's because there's less copying going on there. But recursive action is also very idiosyncratic, as we saw with the implementation that used Java reflection to make an array variable, which is a little bit wacky. And that's particularly true for generics. If you're willing to change the API, then you'll be in better shape. Now, ironically, after going through all this discussion of the different fork join models, the simplest way to use the fork join framework is not to use it directly at all. And in fact, what we do here is we use the parallel stream framework. This is something we haven't talked a whole lot about in this class, but we will cover in next semester's class in the fall. And this is super duper concise. Look what it does. This is so cool. So the signatures are the same that we saw before, except we're not passing in the fork join pool because we don't need to, because there's one implicit with the parallel streams framework, and it uses the common fork join pool. And so all we do is we say, hey, list, turn yourself into a parallel stream. That turns it into a parallel stream automatically. Then we say, please apply the function to every element in the stream in parallel, and then collect the results into a list and return that as the result from the apply parallel stream method. So I think you will hopefully agree with me that this is way more concise than all the implementations we just looked at that use the fork join framework explicitly. And in fact, as it turns out, when we run this, the performance is not too bad. And we'll have some fun and play around with this in a second on my computer here just to see what it does. But it's not bad. In fact, sometimes it works better. So for almost no programming effort, we get results that are pretty much the same with much less work. So what is not to like about that? Well, that's pretty darn cool. And so the real lesson learned here, and this is a lesson that sometimes takes a while to fully grasp, is higher level programming abstractions in the right context can actually perform as well, and in some cases better, than lower level programming abstractions when you're able to take full advantage of parallel computing. And that's what parallel streams does for you. It's kind of magic, but it's handling a lot of stuff under the hood that you don't have to know or care about, and it does it in an optimized way that you may or may not know or care about either, but it knows about because it's written by people whose livelihood depends on optimizing the heck out of parallel programming frameworks in Java. So just kind of a fun way to wrap this up. So that's also sort of a teaser for next semester's class. I think there's might still be a few slots open, although registration is yesterday and today, so it's probably filling up fast. But if you can get into that and you're interested, you'll learn a lot of things in there. So that's the end of our comparing and contrasting with all the different fork-join framework programming models. And the key lesson learned there is sometimes the easiest solution, which is to use parallel streams, is the best solution.